I'm just letting you know, I made a few mistakes in the video while I was trying to do it live that I fix gradually as I realize them. So if you can cope with that, then here's the demo. Okay guys, we're going to be going over how to logger like an absolute pro. I'm just going to do an overview of all the stats involved without the analysis, the written analysis part, because I haven't even done that yet. Real quick before we start, shameless plug, you guys should totally join the Robotics and Tech Club. Our orientation is October 19th, but we run our weekly meetings on Mondays, so you guys should totally join that Google Classroom code. I think you'll really like it. It'll totally help you with physics and with life as well. So if we get started looking at just the uncompleted version, or I haven't touched this, I've just highlighted a couple things. So we need to figure out what she actually wants for the assignment, which is something we've all been struggling with. So here with the analysis, we need this purple stuff is what actually goes on the graph. So we need uncertainties on our points in both directions. We need raw data, which is just going to be so here I'll start writing this down. The raw data is just going to be that parabolic curve we see. This is raw, and there'll be, error bars, however. And then process data is just when we square this bottom thing. So we're going to be looking at u squared, and that will linearize it. What she doesn't mention, but what is in the IB physics videos, is you actually need to include these lines here that are that's the minimum line and the maximum line. What I mean by that is basically, you see all these numbers in this set, right? The black line over there is just the average of each one of these sets plotted on a graph against u squared. What those minimums are you just take the minimum. So here would be 10.5, here would be 19, here 54, and so on, and plot it down there, and then the top one is the maximum, and that just shows that your deviations fall within the range of those minimums and maximum lines. So let's start with getting the actual average values and uncertainties. So if we look at, we'll call it U1 for the first set. What color ranges? I'm going to choose green. It spoke to me. U1 is equal to, I'm not going to put units in them, I'll put them in at the end. 12, 10.5, and another 12. So we want to put in uncertainties for all these. We can do statistical variation later. Statistical variation doesn't actually go on the graph. That's just the percent deviation of the data that we can calculate later. But for now, we're just going to do the graphing. So when you read the question, it talks about a parallax error of the measuring tape. And if you look here, the highest accuracy measuring that we're ever given is to the ½ centimeter. So we're going to assume that they have decided, after running this experiment, that the highest accuracy of a point they could give, because obviously if you have I'll use a different color. If you have a ruler here, and it's got all these like millimeter tick marks, whatever, and the ball lands somewhere here, let's say, they're not going to be able to pin, because they're like standing all the way over here, let's say, and they're observing it all the way up there, or the camera is, I guess. They're not going to be able to tell which exactly millimeter mark it lands on. They're just going to say, okay, generally we've been able to get it within this 0.5 centimeter range, so that's the accuracy we're going to report. So because of that, our inaccuracy, or our error, our measured error, is plus or minus 0.5 centimeters. And
I'm gonna move this. Can I move this? Yeah. Because it's not space. Okay. 10.5 plus or minus 0.5 and 12 plus or minus 0.5. My handwriting with a mouse is honestly not much better than with my hands, but that's whatever. Okay, so now we want to find the average. So how do we propagate these uncertainties when we have an average? Well, first of all, to find the average of any set, just, you know, add them. I won't do sigma notation, but just add them up and divide by numbers in the set, right? So we'll do that. The mean of U1 is, I'll put brackets around all of the inputted data, 0.5 plus 10.5 with the uncertainties plus 12 plus or minus 0.5. All of it divided by 3. Okay? So our first step is to add all of these. If we look in the textbook, you get the rule for adding. So here, for addition and subtraction, if you have A equals B plus C, then the change in A is the change of B plus the change in C. So like, for example, if I want to find the sum of these two things, then the actual number will be 12 plus 10, and the uncertainty of that final number will be 0.5 plus 0.5. So, you know, that'll obviously carry over. So we're just going to add up all these numbers to get 34.5 plus or minus 1.5 all over 3. And then now we have to implement a different rule. Now for multiplication and division, all of it is just you have to divide the uncertainty. So here we have A in this case is our mean of U1. Delta A is what, you know, we're trying to find as a secondary thing. That's just going to be equal to that over U plus that over C. In this case, B and C are both 3. So it's we just divide it by 3 basically in this case because they're both being divided by 3. So yeah, it's simple. When we get into the squaring, it gets weird. I'm pretty sure this was 11.5 or something. Let me check. Yeah. I'm gonna censor that. 0.5. There we go. So this is our final mean for U1. And we're gonna have to go through, well, you could do it automatically with logger, but honestly I wouldn't go through and do that. I think it's better to just, because you have to show this in the assignment anyways, you have to show all of these calculations. So I would just go through and do these calculations manually and then input this into logger as one column and this into logger as a separate column, and I'll show you how to do that now. Let me just save this file. Yeah. So, but this is what we're actually going to put into the logger, and this is what we're going to do for each one of those data points. There were 5 of them to get U, initial velocity. So now, welcome to Logger Pro. This is where it gets weird. So, I'm going to rename the x-axis to be, what was it? Initial velocity, and the short name is just U. Yeah, that's fine. Units, we're gonna do it in meters per second. Negative 1. We're gonna convert it from kilometers per hour. And this is what we just calculated. Did I just mess up? Did I mislabel it? I did mislabel it. That's wonderful. Okay. I knew I was going to make a mistake. I just didn't think it'd be this early. Okay, I just mislabeled. This is not U. This is S. I would love a bigger eraser. I don't know. I don't use this. Okay. Just pretend I did not make this mistake. Guys, it's fine. This is S. This is also totally just S. Did I put that anywhere else? No. Okay. That was S. And for that S, the U1 is 5 kilometers per hour, plus or minus 2, because that's, you know, what's given to us in the equation. So 5.0 kilometers per hour. That's a nice H. Kilometers per hour plus or minus 2.0 kilometers per hour. But obviously we want to convert this into meters per second. So we're going to multiply this by, or no, we're going to divide it, sorry. We're going to divide it by 3.6 to get, we're again, the dividing rule for when you have uncertainties, you just have to divide the number out. So, oh, my PC's bugging out, sorry. Okay, so 5 divided by 3.6, we get that number. That's approximately equal to, let's say, 1.3. It's 2 significant digits, so 1.4. You should show the full number in your calculations, I guess. Meters per second plus or minus 2 divided by that. 2 significant digits will give us 0.56. So 0.56. It's getting cramped, but whatever. 0.56 meters per second. Okay. So now we have this first data point that we can plot. So we're gonna call this one, like you say, we're back. This is gonna be displacement. Short name is just gonna be S, and the units, we're gonna do it in meters, so we can have everything in SI units. We can give the graph a title later, but for now, this U we got was 1.4, and the displacement we got for that was 11.5. And you can see, if I center the graph, if you hit Control J on your keyboard, or you just right click auto scale, then it, you know, there's one point here, so it's going to center that. But if you have multiple points, you just hit Control J, it centers the whole thing. You might want to auto scale from 0 though for now. And the point will be all the way up there, but it'll be better later. But now we want to include this uncertainty, right? So, and this uncertainty may or may not, well, for this case it's not, but for other, when we square it and whatever, the uncertainty is going to be different. So how do we change that? We're just going to go to here, what is this called? Show high data browser. We're going to add a new manual column, because we're putting in these uncertainties manually. And we're going to call it displacement error. Our short name will be, we're going to use this delta S. And our units will, again, just be meters. Done. So we have this other column. I'm going to expand this a little bit. And then shrink this guy. more, actually. We're going to have a lot of columns later. There you go. Okay. So our delta S for this one was 0.5. And for all of these measurements, the uncertainty is 0.5, and for all of them, we only measured it 3 times. So that means across the board, across all of those measurements, it is just going to be 0.5. So we can just copy that down 5 times. But our measured delta S, obviously we have to average everything. Oh, and it's, sorry, this is in meters. So it's actually 0.005 for all of these. And this would be 0.115 for that. And then I can just auto scale, we can see the point. So now we need to do basically the exact same thing. So we need to take the velocity, convert it to meters per second with its uncertainty. Oh yeah, we can include a bar for the uncertainty in the velocity as well. So initial velocity error, we're going to call that, we can use the Greek lower, I think, V of U, and units is going to be meters per second. Oh, per second. Did I make this calculated? I did. It's supposed to be manual. Okay, whatever. I'll copy this because I paint to write. But then I'll cancel. I was supposed to hit new manual column like the last time. Initial velocity error. Right here. Error of U. There you go. We can move this to here. Just physically drag it over. And then we said the error was 0.56, so in meters per second it's 0.56 the error. So there we go. And now how do we add this error onto the graph? What we want to do for the initial velocities, we want to double click this variable, go to options, and over here it says error bar calculations, enable it. You could, for both of these, you could use a constant, but sometimes you won't have a constant. It's just nice to have a work off a column either way, because then you can change it quickly in case it's ever wrong. So here for the initial velocity, we're going to use the initial velocity error for error bars, and you can see we have big wide error bars because it's a lot of it's a big error. And same thing with the displacement here. We're gonna go to options, enable the error bars, use column, displacement error, and that's gonna be super tiny because it is a small error. So now we just need to do those same calculations and write them down in the doc or whatever for all the other data. So I'm just gonna do that super quickly, and I'll cut it so you don't get bored. And I also don't know how to do a time lapse, and I'll get back. Okay, we're back. I put in all these values that should be correct. It doesn't let you say 5.0. It just corrects it to 5. But that's fine. Another thing I want to do real quick before I go further is go into graph options and turn on the point symbols, those little error circles, because those are mainly used for like when you draw a graph by hand or when you do a scatter plot. But here we have like a finite graphing software, so I don't know why it's there. But anyways, so this is the raw data we have, right? And we want to add a curve. So we're going to go over here to curve fit. And we already know that this is going to be a quadratic relation, but if it's not, you can sort of play around with this and hit try fit. And over here we can see for quadratic, we try the fit. The correlation is pretty close to 1. And the root meter squared is also pretty good. We could try. Okay, apparently it's 1 with cubic. I don't know why. I think if you extrapolate it, it would probably wouldn't work because it would pass through 0. But it should be quadratic. So you should try the fit for quadratic, even though cubic is weird. Just do quadratic for this relation because that's what the theory says, right? So I'm gonna hit OK, and we're gonna get this. Oh, we're gonna get this quadratic, and we have this little box here that gives us our A, B, and C values. So this is actually it for presenting our raw data. This is all we needed, right? So we could cross that part of this out, right? Now we want to process it, including the linearized graph and the minimums and maximums, whatever. Okay, it's weird. This is where a lot of people get confused. So if we look back to this guy for multiplication and division. So what are we really doing when we're squaring it? There is technically this rule for squaring it, but I don't like it. So we're just going to do multiplication because really when we're squaring it, we're just doing the multiplication again. So u squared plus or minus delta u squared is u plus or minus delta u times u plus or minus delta u, right? So obviously with the u, for finding u squared, that's just u times u, okay? We don't need to know anything else. But for getting this deviation, if we use, I'm running out of space. If we use the A equals, or where is it? Delta here. Delta A over A equals delta B over B plus delta C over C, right? Yeah. If we use that equation for this, then we get delta u squared over u squared equals delta u over u plus delta u over u. Now from here you can kind of just use basic algebra to find delta u squared, because we have, well, this is just when you're adding to the same thing, you just multiply it by 2 and you can bring this over to the other side. So we get delta u squared equals, multiply this on both sides, u squared times, if we combine that, we get 2 delta u divided by u. And here we can cancel out, I'll use a different color, we can cancel out these two, right? So we're left with, we're left with delta u squared equals 2u delta u. That's how I like to write it. I don't know if there's a proper way, but 2u delta u. So in our case, our deviation, so our, let's say our, for one of them, our initial, we'll just put this in and I'll show you. So delta u is constant. Delta u is always the 2, where is it? The 2 kilometers per hour, or the 0.56 meters per second. So that's going to be a constant. 2 is obviously going to be a constant. So the only thing that's going to be changing is u. So our displacement is actually going to, our error, sorry, for the displacement, when it's squared, our error is actually going to gradually increase. So first of all, I should show you after you square it. You can just, I can get rid of this. You can click over here and choose which variable you want to compare it to. If I want to compare it to initial velocity squared, then bam, now it's linear. but I want to get the errors, obviously. So if I do this, and I make a new calculated column, we're going to call it initial velocity squared displacement. Short name. Did I call it displacement? I should say error. Did I mislabel any other ones? I probably did. Whatever. Here. Greek lower for error. Delta U squared, and then this is going to be that, and our expression is going to be 2 times u, so that's going to be initial velocity. Let me just check the, oh no, I wrote them right, surprisingly. Okay. Times delta u, which is this. Error of u, delta u. I guess I could rewrite them as delta u, actually. That would probably be better if they're deltas than errors. I just did that because it's like parallax error versus error, but that might work better if I do that. Times the initial velocity error. So hit done, we can see this is all of our errors. And I'm gonna quickly, well, I'm gonna move this over here first of all to be beside its corresponding variable, and then I'm gonna change this short form to be this. There you go. Okay, that's a lot better. Save real quick. So now we're gonna add the displacement in the same way we did for the others. We're gonna go to options, error bar calculations, use column, and this is where using the column is actually useful, as opposed to just putting in a constant 0.56 like we could have done for the others. Now we have initial velocity squared error, which is actually changing per each one. You can see it gets bigger and bigger. And you'll see why that happens when we put in the other thing. But for now, we can put in a linear fit. This is just, you don't have to go in here. There's a shortcut for it. You can see the correlation is 0.9998, so it's really close. And that's all we have to do for that. But now we have to put in the minimum and maximum. Okay, so to put in our max and min lines, the way I have done it, the way I'd like to do it is to actually use like the max and min values of the data set. But that's not what it wants you to do. It wants you to basically just go in here, click on linear. You could try fit to just get it in the range, but then you want to hit manual. And I'm gonna increase this slope just a little bit so it's easier. And click OK. If I double click on this, you should get this here that says enable line drag. This only works if it's linear, I believe. So if I click OK on that, you can see these things pop up. So this thing allows me to move the whole line. And what we're gonna try to do is we're gonna try to get it to pass through all of the tops of the horizontal of the vertical uncertainties as best we can, which is weird here because it actually goes below the line. So maybe actually it'd be better to, maybe she wants us to work off of the horizontal uncertainties actually. Yeah, let's try that. Because that would make a lot more sense. Like that. This way it passes through all of those uncertainties while staying as high of a slope as possible. And then we're just going to do and I'll change the color of this. Let's make it tomato. That's a wonderful color. Oh, but now it looks like the uncertainties. No, that was a bad choice. Let's make it pale green. These are such depressing color names. Okay. Our maximum line is now pale green. I'm gonna do the same thing here, linear. tri-fit just to get it, and go down, put the slope down a bit. Okay, not that much. Just to get it in the area, I guess, and then hit OK. This is gonna pop up. We're gonna hit enable line drag, and I'm gonna also make it. I'll make it steel blue. How about that? Steel blue. And we're just gonna do the same thing. So here, we're gonna try to get it to pass through that, and that's gonna pass through there. No, oh, I should clip inside of that, so I'll move it a little bit. And you should see this should be moved a bit too. This should clip inside of all of the uncertainties. I mean, this is normally used for vertical uncertainties, so I'm not exactly sure if this is how it's supposed to be linearized, but this makes the most sense to me than having a maximum bar that's below the average, you know? So that's how we're gonna do it for that. And this is how you completely linearize your data. So if we go back to this demonstration, we have shown it in processed form, and we have graphed the uncertainties and propagated them on both of the variables. Very cool. So now we want to do statistical variation. Most of you guys can probably already do this, so you can kind of just turn it off here. But you know, I don't know if I'll go over it. It's just everybody knows this, how to do this percent statistical deviation. Just message me on Discord, I guess, if that's what you're looking for. But yeah, this is how you set up all your graphs with Logger Pro. I hope I helped and I didn't make too many mistakes that I didn't correct, at least. And I hope this made it, at least it did, I hope this didn't make it more confusing. I hope it at least is a neutral baseline. All right.